All right, let's talk about the future of our electrical grid. We're going to dive into some really fascinating research from IEEE Access that shows it's not just about building more power lines. Nope, it's about building a smarter, more cooperative network to power all of our lives.
So, let me just start with a wild question. What if your house could actually help power your entire city? I know, it sounds a little like sci-fi, but it is way closer than you think. Just imagine for a second, all of our homes with their solar panels and electric cars, all working together as one giant intelligent power plant? That's the big idea we're going to unpack today.
But, to really get why this new idea is so important, we have to talk about the problem it's trying to solve. And honestly, our electric grid faces a problem every single day that looks a whole lot like rush hour traffic.
I mean, think about your own routine, right? It's that time of day when we all get home from work or school. We flip on the lights, we start cooking dinner, maybe throw on a TV show, and bam, the grid feels all of that demand at the exact same time. It's an incredible amount of stress on the entire system.
This crazy busy time actually has a name. It's called peak demand. And for the specific research we're looking at, which was focused on a community in Colorado, this all goes down between 4 p.m. and 9 p.m. You can imagine trying to manage that daily surge is one of the biggest and, frankly, most expensive challenges for utility companies.
So the big question is, how do you solve this daily traffic jam? Well, the answer isn't just to build more huge old-school power plants. It's something way, way smarter: the virtual power plant.
And the building blocks for this whole thing, they're already showing up in our homes and our driveways. They're called distributed energy resources, or DERs for short. We're talking about things like rooftop solar, home batteries, even your EV. And their numbers are just exploding. This research projects we'll have over 200 million of them in the US by 2030. That's a lot.
Now here's where it gets really, really cool. What if you could use some incredibly smart software to connect and coordinate thousands of these little DERs? Well, you can. They can act together, in concerts, like a single, massive, and super flexible power plant. And we call that a virtual power plant. Think of it like an orchestra conductor, bringing thousands of individual instruments together to create one powerful, beautiful symphony.
And this image here shows the idea perfectly. See, a VPP doesn't exist in just one building. It's a network, kind of like a brain in the cloud, that can call on the energy stored in your home's battery, or maybe the battery in your neighbor's electric car, to help stabilize the entire grid right when it's needed the most.
Okay, but just having all these connected devices, all these players, well, it isn't quite enough. You need really smart control systems to manage this incredibly complex dance of energy. And it turns out you don't just need one brain. You actually need two of them working together. These two systems are called ADMS and DERMS. And a simple way to think about it is this. The ADMS is like the grid's air traffic control. It's managing the big picture from way up high. The DERMS, on the other hand, is more like the local dispatcher, coordinating all the resources right there in your neighborhood.
Let's break that down just a little bit more. The ADMS, that's the Advanced Distribution Management System, is the utility's traditional top-down tool. It's been around for a while, managing the big stuff on the power lines. The problem is, it's totally blind to what's happening inside our homes. And that's where the DERMS comes in. It's the specialist, the Distributed Energy Resource Management System, and it's totally focused on talking to and controlling all those residential solar panels and batteries.
So the absolute key, and the researchers really emphasize this, is getting these two systems to talk to each other, to cooperate, making them work as a team. That integration, that's the secret sauce to unlocking the true power of a virtual power plant.
And that's exactly what this whole study wanted to test. But listen, you don't just go and flip a switch on a real city's power grid to try out a new idea. No way. You test it first in a safe but incredibly realistic digital environment.
So the researchers at the National Renewable Energy Laboratory, you'll hear them called NREL, they built what's called a digital twin. It's this amazingly detailed simulation of a real power feeder in Colorado. And this let them test out how this ADMS and DRMS team-up would perform under real-world stress, but without any of the real-world risks. Pretty smart.
And you can see it right here. On the left, that's the map of the actual neighborhood feeder that they modeled. And on the right, that's the advanced lab at NREL, where they ran these super complex simulations in real time. They even included actual physical hardware in the loop to make it as real as possible.
So here's the setup for the experiment. They modeled over 1,100 homes. Then they gave 163 of those homes virtual solar panels and batteries to create their virtual power plant.
They fired up the simulation during that critical peak demand window, and they ran 2 big tests. First, what can the air traffic control do all by itself? And second, what happens when it teams up with a neighborhood local dispatcher?
All right, so what did they find? Well, to put it mildly, the difference was absolutely stunning.
Okay, so in the first test, the ADMS went in solo. It used a pretty standard tool called conservation voltage reduction, which is basically a fancy way of saying it slightly dims the lights across the whole area to save a bit of power. You probably wouldn't even notice it.
And flying solo, it managed to cut peak demand by about 100 kilowatts. You know, that's a respectable number for a traditional tool. Not bad.
But then, they ran the simulation again. This time, the ADMS was working hand in glove with the DERMS, which was in direct control of all those home batteries in the VPP.
And the result this time? A peak demand reduction of nearly 500 kilowatts.
Whoa. Let's just put that into perspective for a second. This chart says it all, right? The coordinated team was 5 times more effective. This wasn't just a little bit better, this was a total game changer. The ADMS did its part by lowering the overall voltage, which meant the home batteries didn't have to discharge as much energy to have the same impact. The whole system just got smarter and way more powerful.
So as you can probably tell, this is so much more than just a cool lab experiment. This research really points directly to the future of our entire energy system.
So why does this matter to you and me? Well, for one, this kind of teamwork creates a much more stable grid, one that's less likely to have blackouts. It also makes it way easier to bring more renewables like wind and solar online. It means we don't have to fire up those expensive, dirty peaker plants every single evening. And maybe the coolest part? It turns us, the homeowners, from just being customers into being active partners in keeping the lights on for everyone.
Ultimately, what this research proves is that the grid of the future isn't about brute force. It's about intelligent cooperation. It's a smart network where our homes, our cars, and the grid itself are all playing for the same team. The technology is already here, so the only real question left is, are we ready to plug in?